Hey everyone, and welcome to The Explainer. Today we're taking the dense, sometimes intimidating world of AWS cloud architecture and tackling it in what I think is the most exciting way possible. We're going to stop thinking about it as abstract code floating on a screen and instead look at it as the process of building a highly organized digital virtual city right from the ground up. Whether we're laying the foundational infrastructure or directing massive crowds of user traffic, it turns out literally every single service has a physical counterpart in our digital metropolis.
All right, here's our roadmap for today's Explainer. We're going to start with the cloud service models, then zoom out to the AWS global architecture, get into building your virtual network, talk about securing the network, and finally wrap up with compute and load balancing.
Okay, let's jump right into Section 1, the cloud service models. These are basically the foundational zoning laws of our digital real estate.
To really understand AWS, we first have to define what cloud computing actually is. Simply put, it's the on-demand delivery of computing resources, networking, and middleware services. And think about how wild this shift is. Gone are the days when companies had to buy and maintain their own incredibly costly physical servers in massive freezing data centers, waiting weeks just to get things set up. Now, you can instantaneously provision resources, and, this is the absolute best part, you pay only for what you actually use.
Now, what's really interesting here is how we can visualize the three tiers of cloud services exactly like real estate. Infrastructure as a service, or IaaS, is like buying the raw land. You get the flexible compute machines, the networking, the hardware, but you still have to build the house yourself. Then, platform as a service, or PaaS, comes in. It builds the foundation and provides the middleware. Think pre-installed database servers, so you don't have to manage all that plumbing. Finally, software as a service, SaaS, gives you the fully furnished software. It's ready to move in and use immediately. When we compare the trade-offs between manual effort and cost, it becomes incredibly clear why you'd choose one over the other. IaaS gives you total flexibility for your computing instances and actually allows you to scale down during off-peak hours to save money. PaaS removes the absolute nightmare of manual middleware patching, licensing, and backup management. And SaaS? It completely eliminates those massive enterprise setup costs, charging you simply based on your user count. It's a total game changer.
Moving on to Section 2, AWS Global Architecture. Let's pull back and look at the actual map of our AWS city. You see, AWS doesn't just exist in the ether. It spans over 32 geographical regions across the globe. Why regions? Well, it's to reduce network latency for local users, adhere to strict government privacy policies, and manage cost factors. And within each of these regions, AWS builds at least 2 availability zones, or AZs. Now, these aren't just separate rooms in the same building. They are totally independent data centers carefully placed to avoid shared power grids, extreme climatic conditions, and natural disasters like cyclones. They are built strictly for high availability. But how do our services actually live in this geography? Well, it depends entirely on their scope. For example, an identity and access management, or IAM user change, is a global rule. You create a user once, and boom, that change applies everywhere, instantaneously across the entire world. However, when you create an EC2 compute instance, that action happens strictly within the local zoning of a specific availability zone. It physically lives in that one specific data center.
All right, Section 3, building your virtual network. It is time to construct some boundaries. Okay, let's dive into this. Welcome to the Virtual Private Cloud, or VPC. This is your isolated network, and it acts as a secure boundary for a specific business project or department. You get a soft limit of 5 VPCs per region. Think of it as a massive, private perimeter fence that spans across all the availability zones in a region, defined by a specific IP network address, like 192.168.0.0. By default, the resources inside this VPC can talk to each other all day long, but absolutely nothing gets in or out without your explicit permission.
Let's move to the next layer and see how this builds out. We obviously can't just throw everything into one giant VPC without some sort of organization. So we break it down into smaller, managed networks called subnets, with a soft limit of up to 200 per VPC. Think of these subnets as the organized streets holding our resources. Crucially, a subnet is tied to a single availability zone. So, to make sure your application doesn't completely crash if a data center goes down, you've got to distribute your subnets across multiple availability zones.
So we have 3 distinct street types in our virtual city. The private subnet is entirely internal. This is perfect for highly sensitive database servers that should quite literally never touch the public internet. The public subnet is attached to an internet gateway. This is your public-facing street for things like load balancers that have to interact with your end users. Finally, we have the hybrid subnet. By using a NAT gateway, resources here can reach out to the external internet to download software updates, but external internet traffic cannot initiate a connection inward. That outbound-only access is a massive security feature and the key takeaway here.
Next up, Section 4, Securing the Network. It's time to meet the traffic cops and the bouncers of our digital city.
So the crucial point here is understanding the difference between your two main firewalls. Network Access Control Lists, or NACLs, are your subnet-level traffic cops. They check everyone entering or leaving the street. They're stateless, which ensures optimal network performance, but that means you have to explicitly write rules allowing both the request in and the response back out. On the other hand, security groups are your stateful bouncers stationed directly at the specific EC2 building doors. Because they're stateful, if they allow an outgoing request, they automatically remember it and allow the incoming response to return.
And this brilliantly illustrates exactly where those firewalls sit in action. Notice the red dashed line of the NACL wrapping the entire public subnet, applying ordered traffic rules to absolutely everything inside. Then, if you look closer at the EC2 instance running our Tomcat application, you see the security group tightly guarding that specific resource, making sure only allowed traffic like HTTP on port 8080 can actually walk through the front door of that specific server.
Finally, we reach Section 5, Compute and Load Balancing. Let's populate this city and manage some serious user traffic. The AWS Compute domain provides the raw underlying engine power for your applications. The absolute workhorses of this platform are Elastic Compute Cloud, or EC2 instances. These are the virtual machines actually running your code. Alongside them, we rely heavily on Elastic Load Balancers to distribute incoming traffic smoothly, and auto-scaling groups to automatically spin up or remove EC2 instances based on real-time demand. Now, I want you to imagine this scenario. Your brand new application goes viral. Thousands of users hit your app at the exact same second. So what does this all mean? How does a single application instance handle a massive influx of users like that? Well, the short answer is, it doesn't. It crashes. And this sets up the absolute necessity for high availability and scalability. We have to distribute our application across multiple EC2 instances, and we need a really smart way to divide up that massive crowd. This is exactly where the Application Load Balancer swoops in to save the day. It acts as the master traffic controller for your web applications. Operating seamlessly right across your public subnets, it reads incoming HTTP requests. Say a user is looking for the path /speed. The load balancer intelligently routes that specific request to a target group of backend servers dedicated just to that function. And it continuously performs health checks on these instances. If one server unexpectedly goes down, traffic is instantly diverted to the healthy ones. Your system never crashes, and the user literally never notices a thing. So, we've laid the foundation, mapped the zoning laws, constructed our secure subnet streets, and set up our master traffic controllers. You now have the complete blueprint of the AWS virtual city. The real question is, how are you going to apply these concepts, the VPCs, those stateful security groups, and the highly available application load balancers to architect and protect your very own resilient cloud city? Thanks for joining me on The Explainer today, and keep building.